derived from this accommodation and statistical model. So, there is an interest in evaluating the optical quality of the eye, and especially the optical quality when we are using bifocal and multifocal optical corrections. But especially these corrections are for myopia correction or for myopia management. And this, the last one, is used in children, and children have accommodation activities. So the interest is to evaluate how this this accommodation is going when we put this type of contact lenses. But when we want to study that, we have to obtain data from children, and children it's difficult to obtain that data and to have a large number of samples. So we decided to construct and build this model. The aim of our study is to reduce wavefront data, applying PCA, that is principal component of analysis, that is a statistical method to reduce the parameters, the dimensions of the data, and then to generate the synthetic wavefront using these functions. So the method that we follow were, first, we obtained these 25 Thornhill coefficients from second order to the sixth order in 6 accommodation levels. These 6 accommodation levels were from 0 diopters, that were the unaccommodated state, to 5 diopters in 1 diopter step, in a total of 191 participants. And the participant ranges were from 18 to 40 years, and these were measured with a commercial aberrometer. So in total we had 115 wavefront parameters, and these parameters had a normal pupil diameter, because the measurements were done under normal conditions without installation of any drug. So any mediatic drug. So we decided to rescale this wavefront in different pupil diameters for its versions, because as we have this near triad of accommodation, that we know that when we are accommodating, the pupil size of our dye is going to decrease. So we calculate this pupil diameter with the 95% of the data, the real data that we obtain for a pupil size, and the other 50% were excluded. So this was a cutoff, and we rescaled all of our wavefronts for each accommodation with this pupil size. But more information about this description of the model and how we obtain the data and the calculation can be found in the poster session of tomorrow. So the method that we follow for applying PCA and then constructing the model was applying the PCA to 115 wavefronts that were explained before, and with this PCA we reduced the dimension to 49 eigenvectors. So these 49 eigenvectors maintain the variance of 99.95% of the original data, and the rest of the data were for a higher order wavefronts. Then we applied a multivariant Gaussian model with expectation maximization algorithm from MATLAB, and we can generate the data for the model. So the results that we obtained for for the eigenvectors were 49 eigenvectors, as I said before, but here I just will present 7 because the higher as we increase the eigenvectors have a mix of the Zernike coefficients, so we're a mix of them, and cannot be found a Zernike coefficient mirror in the wavefront map. So the first one, well, I have to say that in columns are the eigenvectors, and in rows are describing the accommodative demand for its eigenvector. So in first eigenvector, it's mainly formed by the focus. The second, third, and fourth, it's mainly based with information by the astigmatism. And in the sixth and the seventh, it's mainly based with information by the spherical aberration. And here you can see which is the magnitude of its Zernike coefficient that encodes that it's encoding in its eigenvector for its accommodation demand. So the first one, as I said, here are the Zernike coefficients from 0 to 25, so the second one will be the focus, and it's the one that encodes more information. But in the fifth, for example, the encoding information is of more Zernike coefficient, so in the wavefront map we cannot distinguish any trend. So after we have these eigenvectors, we can generate our model, and we decided to generate 1,000 eyes versus 191 original eyes that we have, and in these distributions we can find the Zernike coefficients for the original eyes in solid lines and the generated eyes in dashed lines. So, for example, in the focus, the focus trends to the positive microns with accommodation, and with the generated eyes, the trend is the similar. Also, when we apply statistics, the mean values of the Zernike coefficients were not statistically significant and are more or less the same, and also for standard deviation. This also happened for spherical aberration. As we know, the spherical aberrations become shift to negatives when the accommodation is when the eye is accommodating, and with the generated eyes, the distributions were similar. So, as a conclusion, this statistical wavefront model that it's incorporating accommodation successfully generates these synthetic wavefronts with these 6 different accommodative demand levels. These synthetic wavefronts produce that the model are statistically indistinguishable from the original data. Also, the model effectively maintains the variability of the crucial accommodative Zernike as the focus under spherical aberration, and this demonstrates that the model's ability to operate replicate the natural variability of the wavefronts and can be applied in further research or applications. But the next step that we will go through is to fit different designs of myopia control lenses to test these synthetic wavefront eyes with direct summation of the different types of myopia control lens that are commercially available in the market, and to show how this accommodation interacts with this type of designs. Thank you.
Yes, please stay. Thank you so much, María. The paper is now open for questions.
So you had a large age range. Did you look at it as a function of age?
You had a very large age range.
Yes.
Did you look at it as a function of age also?
Yes, we look at the accommodation, if the accommodation was activated at that age and they can perform this task that was accommodating.
I'm more interested, did the distributions change as a function of age?
Yeah, but what we want is to do it with the accommodation, when the eye is still accommodating, not depending on the age. Yes. Barbara?
Yes, I have questions as well.
Don't worry.
No, I was wondering if you had any independent measure of how accurately the patients or subjects accommodated to those demands. Well, there might have been some accommodative lag involved in the final results.
Yeah, well, we did a pilot study before the final measurements about how they change if we did 3 measurements or just 1 measurement, and was more repeatable if we do just 1 and was more accurate. So that's just the thing that we put just one measurement. But also, I know that lab is present also because it's a commercial device and it's we cannot measure more about that.
That's a lovely talk, thanks. But could you go back a couple of slides to the comparisons you made with original data and generated data? That one. So I think this is really fascinating. Unless I'm not seeing it properly, it seems like the original data has a sharper peak and the generated data has a more gradual peak. Is that right, or is it just that I can't see it well enough?
Yes, that happens in some Wernicke coefficients, but not in all of them. Also, generated data have more data than the original one, so...
That explains it, okay, because I would have instinctively thought that the generated would be sharper, but you've explained, so you've had more points to interpolate in the generated.
It's a bi-Gaussian model, so it's an approximation.
I see.
The sharpness of the peak would need a third or a fourth Gaussian.
I see.
It's really not worried.
Okay, thank you.
This one does work. I actually have the same question, and maybe I'll put it in a simple terms. What kind of estimator have you used to calculate your probability density function? Are these like some kind of scaled histograms, or this is like a kernel density estimator?
It's a percentage of the data that are present in its value of the Wernicke coefficient, but are normalized to show that for generated it's similar to the original.
Okay, but what was the mechanism to generate? Because those peaks that you get are actually curious. That's why, you know, you've got those questions here. Normally when you take a histogram or when you calculate kernel density estimator, your function would be relatively smooth. So the question is, how did you, what kind of tool, or maybe like this, what kind of tool have you used to generate those pictures?
Generate a picture.
Or what kind of tool have you used to present that picture?
Was MATLAB.
Okay, good. That's it. We get it. Okay, but what function in MATLAB produced those plots?
It's an algorithm. It's called expectation and maximization algorithm.
Okay.
But it's from big Gaussian functions.
Okay, so these are some kind of approximation of a normal function, right?
Yeah.
Okay, thank you.
Yes, let's thank Maria again
Thank
and
you.
move on to the next one.
Well, good morning, everyone. It's great to be back in Rostov. It's been a long time for me, but it's great to see both familiar faces as well as so many new people in the field that are coming into it. And in a sense, my presentation this morning is directed at the new people because I want to investigate or discuss an old question that many people already have a firm idea about, but I'm not quite so sure that the firm view is fully justified. So the question is axial versus refractive the best way to think about refractive error? So it's commonly said in textbooks, and you read about it in the literature, that there's this opposing forces. There's a refractive type of refractive error, and there's an axial type of refractive error. And you might often hear people say that most myopia, for example, is axial. But this seems to be a rather simplified view, because the eye is a really complicated optical system, and isn't really just two factors involved here. And if it's so simple, why do we keep arguing about this every 2 years in the VPO meetings? It seems like it might be an oversimplification to think that there's just this dichotomy between axial and refractive parameters. And the comments that I'll make about refractive error really generalize to, and more generally to refractive state. So like what I say about refractive error could also be applied to accommodation. Well, I think that there's actually a very strong precedent for thinking this way. And it comes from some of the best minds in the history of vision science and optics, starting with Christian Huygens, who used what we call a simplified eye. Get rid of all the complexity of an eye to begin with. Just think of it as a volume of water with a refracting surface. And he used that as a way of convincing himself and others that the eye really is an optical system that casts an image onto the retina. A lot of people didn't believe that at the time. And so he was able to make use of this very simple model to make that argument. Listing developed, he called it the reduced eye, in order to basically use the same kind of model to quantify refractive error. And then Helmholtz came along and he used the same kind of model to talk about how refractive error varies with wavelength. So it's got a long history using this simple model. And this kind of model leads naturally to the idea that there's a refractive versus axial competition between these two forces to see which is the stronger, which one is responsible for developing refractive error. So this model is so simple, there are only a few parameters involved. In fact, there's only 4, one of which is outside the eye, the refractive index of the medium that the eye is immersed in, typically air, but it could be water or something else. And then what do we have? We have the refractive index inside the eye, the ocular medium. We have the radius of curvature for that refracting surface. And then we have the distance between the refracting surface and the retina surface. So just 3 optical parameters, or ocular parameters, and one more makes 4 altogether. And from those 4 parameters, you can calculate the refractive power of that refracting surface, change the refractive index divided by the radius of curvature. And you can also determine the dioptric length of the eye by taking the physical length, the distance between the refracting surface and the retina, and divide and put that in the denominator. So it's the refractive index divided by that distance, and now you know the dioptric length of the eye. And refractive error is simply the difference between those two quantities, between the refractive power of that surface and the dioptric length of the eye. So this model is indeed simple, and it sort of supports the idea that it's either refractive, that first surface, or it's axial, the length, the distance between those two surfaces. Yeah. But if you try to pursue that idea a little bit further, you would find although that optical model could be a very good and very useful predictor of refractive error and so on, if you want to take the next step and ask what anatomical feature is responsible for that refractive error that you just measured, that is a more difficult problem because the reduced eye is anatomically incorrect. It doesn't have a lens. It doesn't have a lens. So this anatomical model is much closer to reality. This is the way eyes are actually built. And you could use a model like this to, say, do ray tracing and find out the refractive error and so on. But you need a lot more parameters. Now, you need to have, well, now there are some 5 refractive indices involved. There are 4 radii of curvature, the anterior surface of the cornea, the posterior surface of the cornea, the anterior and posterior of the crystalline lens, and then you have 5 distances involved where all these surfaces are located. So you're now up to 14 parameters. It's becoming a lot more complicated problem. And what we need to do is establish a link between the reality, this anatomical reality, and that simple reduced eye. Because it's a reduced eye that tells us that there's just this difference between 2 factors. But how do you get those 2 factors out from a complicated anatomical area like this optical system? Well, the guy who figured it out was Gauss, a great mathematician and astronomer in the 19th century. And he was in the middle of a period of history when optics was a very active field, just learning how optical systems work. And he came up with a very simple system for doing it. He said, I can do that. I'll connect this to the reduced eye. 3-step process, not a problem. Step number 1. First, you have to tell me these anatomical dimensions. That's like what we call biometric data now. We need to know all those 14 parameters. But if you give me those 14 parameters, I can define for you what's called principal planes and principal points, and these represent where the optical behavior of the crystalline lens and the cornea reside. So let's see if I make this one. Back up here. I'll put my pointer up. I see. So there's a pair of principal planes here, and the idea is, in concept, is light comes in from some object, and it arrives with a certain vergence at the first principal plane. And then it leaves that lens from the second principal plane. They're separate planes. And it's a mathematical idealization here, and sometimes the second principal plane comes first. But don't let that worry you, it's just a mathematical convention to make sure you get the right answer. Right? And so you can calculate very easily what the vergence of the light leaving is. It's simply the sum of what comes in, the vergence coming in, plus the power of that lens. And so that's an equivalent power of that corneal surface, and there is an equivalent power of the crystalline lens as well. Right? So we now have an optical model. It's not anatomical anymore, it's more mathematical and optical, and there are about 10 parameters. And there's basically 4 of these so-called cardinal points. You got the principal planes and the focal points, and then you have the equivalent power for that element. Given those 10 numbers, you can take the second step. That's step 1. Step 2 is, there we are. Step 2 is to look at this now in a very abstract sort of way and say, well, we've got 2 sets of principal planes. Let's reduce them to 1. And the method that he developed was so general, it's quite easy to take 2 sets of principal planes and reduce them to a single principal set. And so that's the so-called, I call it a G1 model, to remind myself, Gauss deserves credit for this. This is his one surface model. And what's beautiful about this whole analysis is I think of as Gauss's law, and that says that these two models, the one at the top, which is more closer to the anatomy, we've got two lenses, it will produce an image of an object of a certain size at a certain place. And the G1 model will give you an image of exactly the same size and exactly the same location. So in that sense then, these two models are equivalent. They're optically equivalent. They generate the same image, same place, same size. Now if we take one more step and sort of ignore the small distance here between these two principal planes in the G1 model, you can end up at a reduced eye, because that's where you put the refracting surface of the reduced eye, halfway between those two principal planes. And so now we have this lovely situation where we have two sort of physical or anatomical models, the real one at the top, the simplified one at the bottom. But they can be represented optically for optical analysis by Gauss's principal plane method. So that is essentially the approach that he used. And if I was teaching optometry students anymore, I'd flash up this curve, this data slide, and no, equations, no, I don't want equations. Back off. I'm not going to go through these, except to say that the method is all based on Gauss's analysis of a thick lens. And in a computer program these days, you can easily just get that program running and you analyze it in a series, step after step after step. Cover those 3 steps, and you've got a reduced eye model. So, for today's purposes, I'm not going to go through all that kind of stuff. I'm going to cut right to the bottom line and show you an equation that shows you how the equivalent power and the equivalent length of the reduced eye depend upon the input 14 parameters. Okay? So, hold your breath. This is the equation. It's a really complicated equation. And there are 13 of the 14 anatomical parameters are in that equation. I've circled some of them so you can see that all 5 refractive indices are in there, multiple times actually. 4 of the 5 axial locations are present. The only one that's missing is the retina, because the retina is irrelevant. This location is irrelevant to the equivalent power of that refracting surface. So that's the one that's missing. And then all 4 radii of curvature are involved in that equation. Similarly, you can get a complicated equation for the equivalent length of the eye, of this reduced eye. And this is even bigger and more complicated. And all 14 parameters are not present. See? So we thought we had a really simple system, and we got these 2 opposing forces, refractive power, axial length, just subtract one from the other. So I have to subtract those 2 equations from each other. It's going to be a little bit complicated. But computers these days can do this quite easily, and so I will just summarize what I'm going to try with the conceptual points, and then I'll show you an example. Is that the equivalent length of this reduced eye is affected by all 14 anatomical parameters of an anatomical eye. Equivalent power is by all except 1. So consequently, the axial length and refractive contributions to refracted error are not independent of each other. They depend upon the same set of parameters, so in a sense correlated variables. And with only one exception, every structural parameter in the anatomical schematic eye affects both the power and length. Every parameter, you go in there and start playing now and say, I'm going to adjust this anatomical parameter. It affects both length and power. So typically, each structural parameter affects both, but one perhaps more than the other. And sometimes they have the same sign, sometimes they have opposite signs. So since most anatomical parameters of the eye will change over an individual's lifespan, it's going to take some comprehension of all these anatomical parameters, which are changing with time, how they end up affecting the final refractive error or refractive state of the eye. So a quick example. Let us take that anatomical eye and we'll change 2 parameters. Those 2 will be the position of the anterior and posterior surface of the lens. All right? So I'm going to keep them at the same separation. I'm just going to move the lens inside the eye. We might say that is adjusting the depth of the anterior chamber. Anterior chamber is going to change. So if you adjust the anterior chamber, that's the x-axis on this graph, anterior chamber depth, and reduce all these numbers down to a reduced eye model, now just look at how equivalent power changes, for example. Well, equivalent power is the blue one, and it shows the equivalent power is dropping. Well, that Gauss said that's how it works, just because the more you separate two positive lenses, the less power you have. So it's trending in the hyperopic direction. Meanwhile, the principal points are moving around, and so they're changing, but in the opposite direction, because the principal points are moving closer to the retina, small distance, dioptrically it's a large number. And the difference between those two is then to be huge. All right, I will finish with one further point I really need to make. It's a kind of inconvenient truth, and that is that the refractive error of it varies with scale. You see, there's something very missing, a very important thing that's missing from this figure. It's laid out the structure of the system beautifully, but there's no scale bar. You don't know if this is a small eye or a big eye, right? So let's suppose that this is a large eye, an adult eye. All the distances here are relatively big, including the distance to the far point, which is another way of thinking about refractive error. Far point's a long ways away. That means there's a small refractive error in diopters. Whereas if this was a child's eye or even an infant eye, all the dimensions would be small, including the distance to the far point. It's a small distance, therefore it's a large refractive error. So here we have the same physical structure of the optical system, and it has a different refractive error depending upon scale, its size. And that seems to me to be a problem for those of us who are interested in discovering the structural basis of refractive error, because it changes with size. So how are you going to get around that? Well, a very simple approach, there's lots of ways of doing this. What I'm toying with at the moment with my colleagues is to do a very simple process of normalizing refractive error by the equivalent power of that reduced eye. And if you do that and look through the equation there, you'll find out that refractive error, the normalized refractive error now is the ratio of dioptric length to equivalent power. K prime over L. It's the ratio, not the difference. It's the ratio. And that ratio is independent of scale. So this becomes now a unitless measure of refractive error, independent of scale, and so it has the potential to make the analysis of the growth of an eye simpler and more tractable. And just to give you a simple example, I've got, again, the anterior chamber depth. Let's suppose that it varies linearly, it's just hypothetically, varies linearly with age. And through that change, it starts out a hyperopic eye, and that hyperopic eye gets smaller, less and less refractive error, as we said, simply because it grew. But now, here's the change from uniform growth, and let's suppose something happens at age 3, and for some reason, we don't know why, the anterior chamber starts to grow faster than the rest of the eye. So now it's non-uniform growth. And when you do that, look, you see what happens to the, it's going to be complicated if you just look at refractive error, because one factor is making hyperopia decline, but then because the anterior chamber is growing, it's going to be more hyperopia. So it's really complicated. But if you normalize the data, you just see a simple step change. It's constant during this period of a uniform growth, and then it jumps up to a new value because the growth becomes non-uniform. So just an example, perhaps a way of approaching longitudinal data of an eye to see how the structural changes are happening. So to summarize that part, unlike conventional refractive error, the difference, which is the difference between axial and refractive factors, the ratio is not affected by uniform growth of the eye. So the normalized error seems to me to be better able to reveal patterns of non-uniform growth that are responsible for changes in refractive error, refractive state in general. So I will finish with a link to the software that Matt Jaskowski wrote to enable me to do this project, and it's available on this platform called GitHub, which is a place where people can get access to software free of charge, modify it, make it better, spread it out back out to the community. So it's open source development platform. That's where it is at the moment. So, if there are any questions or comments, even if I have some time left over, which I probably don't.
Thank you so much, Larry. One quick question for Larry. Yes, this one.
I do have.
Yeah, then we have one waiting for us.
Thank you very much for a very interesting presentation. But the Gaussian optics I use in everyday classes, but it is still a paraxial approximation. Do you think that we should go more into a real representation, a three-dimensional representation of the surfaces, and to think about the refractive error as something that is much more complicated? It's not only paraxial, because then we could take into account, for example, a non-parallel axis of these all elements, non-uniform distribution of the refractive indices. So how far should we go to the real representation of an eye to better understand the refractive error? Because if we concentrate, if we focus only on the axis of this whole system, we probably, I'm not sure, we probably miss some information about the, for example, development of myopia, as you gave as an example. And the second question is maybe a comment. I think that this differentiation between the refractive origins or the axial origins of myopia, for example, and other refractive errors is important in the clinical practice, because we know that the probability of some pathological changes in our eye are strongly connected with the type of this refractive error. And then the actual number, the actual error, numerical error, is not so important as the type of this error. And it's not for optometry specialists, it's more for the ophthalmology specialists, of course. But I think that these two types still should be taken into account in real cases.
Thank you. I think there was a comment.
The first one was a question.
My ears don't work very well, so I'm not sure if there was a question or that was a comment. But
the second one was...
the first one was asking how far you need to go in modeling. Is it enough with paraxial optics, or should we go to third order?
Oh, I see what you mean. Yes, well, this is, if I understand that, the question is really about whether or not this paraxial analysis is sufficient. Because this is, all this Gaussian stuff is paraxial. We're assuming the rays are very close to the optical axis. But there is a much broader question about how the optical system of the eye changes as you get outside the paraxial domain. And that's a whole other ballgame out there, because we have to answer the question now, what do you mean by best focused when you have an aberrated eye, where those aberrations are contributing to the retinal image? So this analysis is much more concentrated on a very simple-minded idea that we're talking about paraxial rays, and any aberrations are just not involved. We don't consider them. Not that they shouldn't be, but in this analysis they're not. So it's a simplified analysis.
Okay. I just thought that Gauss would expect to go more into our technical possibilities nowadays, but okay.
Yeah.
It's very important.
It's important
basic analysis.
when we
Okay,
need
thank
to
you very much.
leave this discussion for the break. Yeah, let's thank Larry properly now.
Hello everyone, I'm Hosna Ghaderi and I'm a PhD student at the University of Antwerp under the supervision of Professor Jos Roseman. Today I would like to present our result on simulating keratoconus development on emmetropic eyes. Well, I assume that all of you know about the keratoconus, a disease which the cornea becomes structurally and locally weak, and resulted in a cone shape and bulge up. So it causes many optical problems, such as astigmatism or myopia. Different factors are involving in onset or progression of keratoconus, for example, like genetic factors or systematic or behavioral factor like eye rubbing, but still yet to be completely understood.
So here we want to analyze what is the influence of initial shape of the cornea in the keratoconus development. Actually, we want to see how different emmetropic cornea are responding to the same structural weak spot. So for the method, we chose 5 emmetropic cornea from synthetic OBM model, which this model is developed by me and Professor Zema at our lab in Antwerp. We chose actually 5 emmetropic cornea from this database, but I want to explain a bit briefly how these corneas are created in this model. These corneas actually are creating from Zernike coefficients, which these Zernike coefficients are converting to the point cloud, but as it was like over 6.5 millimeter diameter, we extrapolated by fitting the quadratic surface to these surfaces. And then the original, the central part of the fitted surface was replaced with the original data, which was the Zernike elevation. And then as it was an intersection it was a junction in that intersection between the original and the fitted surface, we used the smoothing algorithm to smooth that area for better optical and mechanical simulations. The outcome of the models is a mesh. So we converted those IMP meshes to ANSYS to simulate the keratoconus, and for the material properties, we assigned Hookean material properties but fiber independent. And the mesh was already tetrahedral mesh, but we did remesh to do the mesh convergence. And also for the boundary condition, the edge of the cornea was fixed and the IOP was considered as a 16 mercury. So for the development of keratoconus, first of all, we obtained a stress-free configuration of the cornea. We know that already cornea is under pressure due to the IOP and it's under retention, but what is the geometry of the cornea if the IOP is absent? We used the iterative method in ANSYS to obtain the cornea geometry in absence of the IOP, and for developing the weak spot, actually we considered different scenarios. For example, we consider central and inferior keratoconus with different diameter, 2 millimeter and 4 millimeter diameter of the weak spot, and also a transition zone. To inducing the weak spot, we also considered 2 different methods. First method was linear gradient, which is in blue at the graph. And this method is starting from the center of to increasing the stiffness of the weak spot, from the center of the weak spot to the boundary which reached the healthy cornea. And the amount of the reduction was from 25% of the healthy cornea till it reaches the 100%, which was the healthy cornea. In the second method, that it was a uniform center method, we considered the fixed diameter of the weak spot and then a transition zone, which is indicating in red in the diagram. And then we pressurized the corneas to see how they will respond to this structural weak spot. So, as a result, if you can see, here is the tangential curvature maps of these different scenarios and corneas. The first column is indicating the tangential curvature map for healthy corneas, and after that is for central and inferior keratoconus with different diameter. As you can see, although the initial curvature map is different, they will respond differently as well. So we are observing actually different patterns to the same structural weak spot. In this method, which was the first method, the linear gradient method, it's indicating mild to moderate keratoconus, which the range was the difference between the pathologic cornea and also the healthy cornea was between 2 diopter, the differences, till like 15 diopters. In the next method, the second method, which was the uniform center method, we observed also different patterns to responding to this weak spot. And this method actually indicating more severe keratoconus, which also the range was between, the differences between these 5 emmetropic corneas was between 13 and 17 diopter. But how these differences are related to the initial parameters, like central cornea thickness or the initial anterior curvature. So we analyzed all of the cases with the different methods and with different diameters, and as you can see, there is like a fluctuation pattern between these corneas, these responses. But as we just analyzed 5 cases, we can't say that much about the relation between the initial parameters and also the response of to the weak spot. But let's go back to the inferior keratoconus that we developed for different diameters. For those who are familiar with keratoconus, you can see that the pattern is like pellucid marginal degeneration. So to investigate this more, we analyze more set of analyses. First of all, we performed many analyses for the developing the weak spot from, as you can see, in this pictures, it's for anterior and posterior tangential curvature map, and 100% means that healthy cornea and the stiffness in the weak spot in the inferior actually keratoconus starts to decrease till 25% of the healthy cornea. As you can see, in the center of the weak spot, strong curvature is creating, which this curvature is dependent, of course, it's dependent on the stiffness reduction, but also, sorry, it's it's dependent on the size of the weak spot as well. So here, in the other set of analysis, you can see that the size of the weak spot is starting from 0, which means healthy cornea, to 4 millimeter diameter of the weak spot. And also this will follow the position of the weak spot from the center to the 2.5 millimeter down for inferior cornea. So our results is suggesting that maybe the pellucid marginal degeneration is another form of keratoconus. So as a conclusion, actually our conclusion, it's a bit obvious that the corneal topography is affected by the weak spot, but also is dependent on the initial shape of the corneal topography before the disease. And also we can say that, it's also affecting the initial shape of the keratoconus, the corneal topography before the disease. And as we can say, we can't say that much about it, because if the patients only go to the doctors when there is a problem. So when they go to the doctor, there is already a disease or the problem there. So we don't know how was the initial condition of the cornea before the disease. And since we don't have that much information about that, because of the synthesis, we can try different scenario and different things on exactly the same cornea to see how is the pattern, or if we can find a pattern out there. Thank you so much.
Thank you so much, Hosna. So, questions?
Thank you. I have a comment and a question. The comment is that when you present the data related to biomechanical engineering, it would be good always in simulations that you tell us what were the material properties and what were the boundary conditions, because depending on that, that would be sort of, right?
Actually, I referred to, maybe I didn't say what is the exact the exact material properties, but I indicated a bit about I showed a bit about the bonding condition. But
Sure. You said software you use, but I'm talking about whether you use what kind of material properties. Have you decided that the material is viscoelastic or whether the material is linear?
Yeah, actually, I use Hocken hyperelastic material.
Okay. And the boundary conditions. Oh, it's there.
Yeah.
Okay. Thank you. Mea culpa. Okay, another question to the slide about the changes in CCT, because I didn't understand that. You're looking at fairly healthy corneas, right? From 520 to 580 micrometers. So where is that simulation of keratoconus coming into play?
Yeah, actually, these results is about, for example, the CCT is indicating before the keratoconus. So we are saying the initial, for example, parameters is for the thickness is from 0.52 to 0.58. So this is the initial, but we didn't show how much is the thickness reduction due to the keratoconus.
Okay, that would help.
Yes, because we wanted to show here that what is the relation between the initial parameters and the changes after keratoconus.
Okay. And KTC stands for what?
Yeah, keratoconus.
Just keratoconus?
Yes.
Okay.
Central keratoconus with, for example, 2 millimeter or 4 millimeter diameter.
Okay, thank you.
Yeah. Thank you for your question.
I have two questions. Just curiously, do you know any studies or any study that shows what's the most frequent site, the position of this weakening spot within the human population? What's the most frequent? Did anyone show or not? Yes. Okay. So the second question is, did you check what's the impact of IOP on the patterns that you show?
No, actually, we just considered IOP as a fixed, like 60 mercury, but we can consider that for later studies.
I also have a comment for you. I wonder, you said that there was one of the difficulties was to know what the initial cornea shape was before the keratoconus started. Could you use the fellow eye to get some clue of that?
To use what?
The other eye, if the other eye is healthy. Could you use some mirror symmetry there?
Actually, I think these corneas are just the right eyes, so we didn't simulate that. And this is not patient-specific data, but I mean, the geometry of the corneas and the data we use is just close to the real data, but it's just for the right eyes and the data. Thank you.
Yes, in that case, we thank you, Hosna. Okay.
Good morning. After the last DPO, Joss and I were chatting about transferences or system matrices, and Joss's question to me was, but what do A, B, C, and D represent? Now, Bill Harris will tell you that they are the fundamental optical properties of an optical system, and my analogy is that they are the building blocks from which you can obtain all the usual familiar optical properties of a system. So the familiar properties are, well, we know that power, front vertex power, back vertex power, Prentice's rule, refractive compensation, positions of the cardinal points, divergence across a system, thick lens power, etc., etc. So then we say, all right, let's simplify this and let's have a look at just the cornea. And we then change our system, so we're looking at just the cornea, and we obtain the transference. So you'll see we've got the three matrices. We start multiplying in reverse with the front surface power, the reduced thickness, and the back surface power, and that gives us a matrix that looks like that. So what we did is we then said, all right, let's create topographical maps of C and D, and let's see where this takes us. Let's see what it's representing, if we can see something in the maps. So we use the point-by-point pentacam data, which gives you a grid of 141 by 141, and obviously we take the corners out, and it will reduce to approximately 7,000 to 12,000 points for a cornea. We then treated each point as a system and obtained its transference and compared this to the pentacam maps. So that is what you're seeing. We've got A, B, C, and D. And we then looked at the transference and we said, all right, well, position B looks the simplest. It's the reduced thickness. And so if we compare it to the pentacam map, we've got a fairly strong similarity with a scaling factor of 1/n. We then dug a bit deeper, and if we look at position C, we can see what looks like the thick lens equation or the Goldstone equation, and bearing in mind that for a transference, the C is equal to minus F, the negative of power, and so then we've got thick lens power, or what the pentacam calls the total power. So if we compare the two maps, they are the same, with the exception that there's a minus sign difference between the two. We then said, all right, we need to dig a little bit deeper into the A and the D position, and if we look at A, we can see there's an influence of the reduced thickness as well as the front surface power. And so there is the front surface power map for us to compare. And then we said, all right, let's just pull this apart a little bit and manipulate. And for those that were at the previous VPO, you'll remember Cynthia Roberts introduced corneal contribution to stress, which is based on the hoop stress equation without the component of pressure. And that is what it looks like. It's the radius of curvature over 2 times the thickness. And so we said, all right, hold on, there's something happening here. So if we manipulate a little bit, we can see that A is somehow related to the CCS, as well as a constant based on the refractive indices. So we take the refractive indices for the pentacam and we get a constant. And that is what the CCS map looks like, which we can then compare to A. Comparing those two. Right, so if we look at D, we can see there's a strong similarity to A. However, this time it's based on the back surface power. And there is your back surface map. And if we manipulate a little bit, we can see that there is some sort of CCS component, but mechanically it can't be CCS because it has to be on the outer surface. And so we've called it second surface contribution, some sort of CCS-like aspect that's coming in to our maps. So, because this is an exploratory study, we had a look at keratoconus, and we've got our ABCD maps, we've got pachymetry, we've got CCS, anterior surface to compare to A, we've got posterior surface to compare to D, we've got total power compared to C, and pachymetry compared to B. And similarly for form thrust, anterior power and CCS compared to A, pachymetry and B, back surface power and D, and total power and C. And then we said, all right, let's have a look a little bit more. We know the transference is a symplectic matrix, which for a 2x2 matrix really just means that it has unit determinant. So we can have a look at AD and CB, and we see that there's an element of the reduced thickness as well as the power, or C. The trace is A plus D, and that gives us 2 minus tau, or reduced thickness, times the thin lens power, or true net power, as it's listed on the pentacam. And if we manipulate, we can see that the trace is going to have an element of CCS and SSC involved. So there is our summary. The first column is the trace, it's A plus D. The second column is A times D, and the third column is B times C. And those are the same three eyes, our normal healthy eye, our keratoconic eye, and our form thrust eye. And we can see those keratoconic circles coming through very nicely in the ABCD, and the trace and the determinant. So in conclusion, we set out to sort of really understand what ABCD is, as opposed to some new way of defining or determining keratoconus. What we found may be coincidental. We need to investigate that a little bit. And the topographical maps, if A position A or dilation is related to CCS, B is related to pachymetry with a refractive index scale, C will be the negative of the total power, and D is related to SSC. And for any system other than the cornea, please remember that A, B, C, D are the building blocks to the familiar optical properties and shouldn't be seen in isolation. And seeing as we're in the city of dwarfs, we can build our building blocks out of Lego dwarfs.
Thank you so much, Tanya. We have time for questions.
Tanya, thank you. I was wondering how much the tau value is important in the study. I mean that because the cornea is so thin that maybe when you include just an identity matrix instead of tau, that will change the results very much or not?
Well, it's basically bringing in the same values as pachymetry. So depending on how even your thickness is or how just uneven it is in keratoconus will tell you how much it's going to affect.
I don't know, have you tried to just put an identity matrix and see the results will be very different from the experimental data?
Sorry, I didn't understand that.
Yes, when you do your matrix, okay, you are taking tau not as identity matrix, okay, because it's so, and then you compare your results with the topography of the given by the topographer. It will be very different or not when you are considering this thickness.
At this point, we basically were exploring where the ABCD are taking us. I think what you're asking is going to be the next step, is to have a look at the data on a large number of eyes and see what the effects are.
Okay. So I'm going to follow up on Roberto's question. So his question was, if I interpreted it right, if you just ignore thickness and use the corneal first surface, are your differences large compared to using both the front and back? If you just, could you, trying to find out how important the variation in thickness is, I think was his question.
if you only look at one surface, you're going to get the exact results as what the Betacam is giving you.
I tend to agree with you.
Yeah, thanks for reminding
That's
us.
actually very interesting work, Tanya, but there was a question at the back. Sorry.
So Tanya, I'm just, if I've seen it properly, one of your keratoconics, your generations maps shows that A times D is similar to B times C. And I just wondered what the meaning of that was. I think it's the name of a couple of slides.
A times D and
if I'm reading it properly, when you show the maps of
this one.
Yes. I mean, yes, that one, the little one. So what's the meaning of that? What's the significance of that? It just looks so similar. You say SSC and CCS multiplied, it's the same as pachymetry, and that's correct, is it?
If we look at the formulae, you'll see that A times D and C times B, because of the symplectic relationship, they are going to be very similar because they're both based on reduced thickness and C, which is the negative total power. So they are going to be very similar just with that scale of the addition of 1, the unit of 1. If we look at the trace, that is actually more interesting because you've got the influence of CCS coming from the front surface, as well as the influence of SSC coming from the back surface. So it's combining a CCS-like component that Cynthia introduced last year, but for both back and front surfaces. And we know that keratoconus usually starts on the back surface, so it may well be interesting clinically that we still need to work out.
That's fascinating because it might tell you something about the difference between the surface and the development of keratoconus. I think this has got massive clinical applications. Thank you.
Thanks, Barbara.
Just a quick question. The P mean that you have for the keratoconus and form frusty, what does it signify, that parameter? P mean.
P mean?
Yeah. You've got that on the slides where you show first, let's say, keratoconus. Yeah, here, for example.
Okay,
what's that P mean?
Minimum thickness.
Okay.
Chemistry that
Okay, so is that like a CCT or where do you measure that?
So these are actual people, actual eyes. So this particular one was a 41-year-old male with maximum curvature of 42.33 and minimum thickness from the pachymetry of 539
Okay, so who said that is a keratoconus based on what? So
this is full thrust. So this eye is the
sure, but let's have a look at the keratoconus, right? We've got a keratoconus with 508 micrometers corneal thickness.
Yeah.
So what other criteria other than thickness have been used to diagnose that person as a keratoconic?
As form thrust. Or this one.
This one.
This one. This was a keratoconic patient.
Okay.
He was being
pretty thick cornea to me.
It was very obvious keratoconus, topographic curvatures.
Okay, so it's like but not the thinning of the cornea.
Not the thinning of the cornea, and the contours wasn't that.
Okay. Thank you.
Yeah, so I have a question on the next slide, I think, where you showed the determinant formula, maybe one further. Because you said that it's a symplectic matrix. I don't think that's correct in this case, because it's the determinant is the ratio between the refractive index of the incoming and the outgoing medium, and you come from air and you go to the vitreous. So I don't think it's one in this case.
No, the transference belongs to the Lie group, the symplectic Lie group. But I know there are two ways of defining the system matrix. I can show you. So in order to build our transference, we use reduced thickness, so the refractive index is in the matrix, and power.
Yeah, but the reduction, I think, goes a bit wrong here, because the refractive index in front of the eye is 1, and behind the cornea it's not 1 because it's not error. And then the one you showed after the determinant is the ratio between both indices. But maybe we can discuss after in the coffee break.
Okay.
Yes, much to discuss afterwards. Thank you so much, Tanya. That's really interesting.
Thank you.
Here with this presentation, what I want is to share with you the theory we have been working on. Our objective is to obtain a theoretical framework to get a better understanding, try to get a bigger picture of the refraction in the human eye. For this presentation, I'm going to be using this reduced eye model with that pupil. Our objective is to get, as I said, a better understanding of what's going on with refraction using the Seidel theory and the concept of interaction between axial astigmatism and the oblique astigmatism. We will be reporting the refraction in the exit pupil, and it will be reported with the vector notation using the spherical equivalent and the cross cylinders at 0 and 45 degrees, being these angles the field angle and the meridional angle. And as I said, it will be supported by, first of all, the Seidel theory and also the concept of interaction between the axial and the oblique astigmatism. So, first of all, I would like to talk a little bit about the Seidel theory. As we know, when we want to move from the paraxial optics to get a better understanding of the aberration that is happening in your optical system, we need to move, if we want to continue working in the framework of the geometrical optics, to the theoretical optics of aberrations. There is where we can find this Seidel theory. And what I want to show you here is why it is suitable for this kind of purpose of explaining how the refraction is generated in the human eye. For sure, we know that the Seidel theory has a limitation. It is that it is developed for rotationally symmetrical systems, but we will be using this property and this simplicity for our purposes. So first of all, I would like to show you this wavefront equation from the Seidel theory. And the first thing that we can see is that here we have, when we are describing the wavefront, 3 parameters. We have the rho and theta, the parameters of the pupil, entrance of exit pupil, depending on object or image plane. But the thing that is interesting is these coordinates, the coordinates of the image plane. That is why if we compare with the Seidel, with the thermic wavefront that we usually work with, it just depends on the pupil coordinates. So we define one wavefront for one specific point. With the Seidel theory, we know what is going to be the behavior on the image plane. And also, here we can see the different coefficients that will be related to the spherical aberration, to the chromatic aberration, oblique astigmatism, field curvature, and distortion. For sure, for the refraction, we will be using oblique astigmatism and field curvature. So, here is also the point of the interaction between axial and oblique astigmatism that is nicely explained in the paper of Tao Liu and Larry Thibos, in which we will be using, because with this interaction we can split the contribution of the astigmatism into the axial astigmatism and the oblique astigmatism. So we can divide our problem into 2 different problems, using for sure the cross cylinders. So let's start talking about the axial astigmatism that we use, for sure. When we have different radii of curvature, the light will be mostly split into 2 different points, tangential and sagittal one. So we need to be able to calculate this cross cylinder at 0 and 45 degrees. For doing that, there are different ways. What we did is just propagating 2 different marginal rays at 0 and 90 degrees. Then we have this sagittal and tangential point. With the distances, we are able to calculate the divergences in the exit pupil plane, and then with the difference we can calculate, and the index of refraction, the cylinder at 0 degrees. With the relationship with the cross cylinders, we obtain this expression, so then we are able to calculate this cross cylinder at 0 degrees. If we repeat this process for 45 degrees, propagating a marginal ray at 45 degrees and also at 135 degrees, we can obtain another expression for the cross cylinder at 45 degrees. So now we know the astigmatism, the axial astigmatism, and of course we can obtain the axis. So now let's move to the oblique astigmatism. We know that if we are working with a rotationally symmetrical surface, the light that is going to be propagating through that eye is going to be paraxially to one point, but if we move off axis, we will start to see that appear these tangential and sagittal components for sure, because this surface is axially rotationally symmetrical. But locally, we will see different radii of curvature. Because of this radii of curvature will be appearing this astigmatism, and then if we move, we will see that the image will be generated over two surfaces, the tangential and sagittal surfaces, and if we go to the definition, we will see that the oblique astigmatism is the one produced by an axially symmetric surface. So that is exactly the framework in which you can apply the Seidel theory. For sure, what we will need to be able to do is, we have an astigmatic lens, we need to be able to calculate the equivalent one without astigmatism. This is just to calculate the mean curvature of the surface, so the important point is to have the same spherical equivalent, and then we will be able to apply the Seidel theory. So for applying the Seidel theory, as a little summary, we need to propagate, first of all, a marginal ray coming from an on-axis beam. Then we need to propagate the chief ray from an off-axis beam, so just the propagation of these two beams, and having the information of the height at which it's hitting the surface and also the angle of refraction, together with the geometrical properties of the eye that we are working with, the indexes of refraction, radius of curvature, then we can calculate the Seidel coefficients for the oblique astigmatism and the field curvature. So here we can see the equations. They are not important. They are important if you want to play, but not exactly for the presentation. But then, when we know the Seidel coefficients, we can calculate the radius of curvature of these surfaces, because the Seidel theory will be predicting that the image is generated over an spherical cell, in this case the sagittal and the tangential surfaces, and the radius of curvature will be given by those equations. But for sure, all of these equations I have at the end a bibliography that they are from those books. The interesting point of the Seidel theory is also that this is a reducing model, but we can apply in the same way for a complete eye model, in this case Navarro's eye model, for example, or any other model. The only thing that we need to do is to repeat this process with the different surfaces, and then we have the different Seidel coefficients for the different surfaces, and just is the summation of the different contributions, and then we will have the total Seidel coefficient. And in that way, we will be able to calculate again the radius of curvature of these two surfaces. If we want to calculate, in this case, the cylinder, the divergence of the beam in the exit pupil, we will need to do it following along the chief ray. So what we need to do is to calculate the intersection between the chief ray and the retina, the chief ray and the sagittal and the tangential surfaces. With those distances and the indexes of refraction, we can calculate the divergence errors, the tangential and sagittal divergence errors. With these errors, we can calculate the cylinder with the difference between both, and then with the relationship between the cylinder and the cross cylinders, we can get this expression. So we can obtain this oblique astigmatism. So we see now that we are able to calculate the total astigmatism, we can calculate the axial astigmatism, we can calculate the oblique astigmatism, so now we need to calculate the interaction between both. So for doing that, we know the cross cylinders for 0 and 45 degrees, and then if we want to be working, for example, with the cylinder, we can calculate it for sure. Now, we need to be able to calculate the spherical equivalent. For doing that, we can use the Seidel theory for calculating the spherical equivalent. It is, in this case, as the Seidel theory for rotationally symmetrical surfaces. This spherical equivalent will be rotationally symmetrical, and we will see that this is one limitation that we have, that we will see how it affects in the final results. But for calculating it, we know the divergence errors. It is the circle of least confusion. It will be just the spherical equivalent. It will be in the middle between the tangential and the sagittal surfaces. And now that we know these values, we can calculate the spherical equivalent as well. So like this, we have in this theoretical framework the spherical equivalent, rotationally symmetrical, and then the cross cylinders at 0 and 45 degrees for the field and meridional angles. Now it's the time to show you the validation, in this case using the Navarro's eye model. We use a retina of 12 millimeters, and we substitute the anterior cornea with a toric surface with astigmatism at 30 degrees to have a specific axis different than 0. Again, we also substitute the posterior cornea also with astigmatism, then we apply the theory. And then we take this model and we introduce it into Themax. We apply the proper corrections for the elliptical pupil, and we compare the cylinder and the spherical equivalent given by this theory and also given by Themax. So if we go to see how is the astigmatism from minus 25 to 25 degrees, it's shaped like this. The typical one in which we have here the axis of 30 degrees. These two nodes related to the points in which the interaction between the oblique and the axis astigmatism is compensated in some way. And here we have the results given by Themax. So we see that is quite effective to use the combination of this cellular theory, the interaction between axial and oblique astigmatism to obtain the astigmatism, the cylinder along the field. And here we can see the error. It's less than 0.1 diopters. It is an error that will be motivated also because of the approximations of the theory and also numerical errors that can be found in Themax. So this is the result that we find for cylinder. Let's move to the spherical equivalent. As it comes from the cellular theory, it is rotationally symmetrical. So we have something like this. And now if we apply the Themax, this is what it is going to be expected. The values, the range is the same, but we can see that along the axis of the astigmatism, this surface becomes something like folded because of the contribution of the astigmatism. It is not rotationally symmetrical anymore. We can see that the base is the same, but if we see the error in this region, it's quite a small error, but on the axis of the astigmatism, it becomes much bigger. So, as conclusions, we have seen that by combining the cellular theory with the interaction between the axial and oblique astigmatism, we can simulate refraction, then obtaining the theoretical formalism to increase our knowledge about the origin of it and its correction. But for sure, there are limitations that we have seen. First of all, the kind of surface that we can simulate the spheres, conic, toric, toroids. But when it comes to simulate biconics with different conic constants independent one with each other, appears appears not the same result. Of course, the spherical equivalent is rotationally symmetrical in our case, and it is not. There is this contribution because of the astigmatism. We are working on these days into these two limitations, but this is the shape of the theory that we have nowadays. And also there are a lot of opportunities because we have applied the cellular theory, the basic cellular theory, but there is the cellular theory with tilts, with decentrations, with gradient radial gradient indexes. So we see here a lot of opportunities, and we want to share this theory with you. So thank you so much. And here we have the bibliography. We can, I guess,
Yes, thank you so much. Questions?
Thank you very much for a nice presentation. I was wondering, because optical simulations in Emacs, now you can do anything, right? And it's just quick, takes seconds. So what is the benefit of developing this third order theory now?
The best benefit is to understand what is happening inside of the problem. As all these theories, what you are developing is like a little laboratory in which you can understand what is happening there. When in Themax sometimes you can do a simulation and you obtain a specific result, maybe you don't know what's happening inside of the problem, inside of the system. With this theory, you can understand what is going to interact. Why when you change a specific index of refraction is going to change in a way when you change when you introduce a conic constant, what's happening there. So this is the main, in my case, it's to learn and to increase the knowledge. But for sure, if you're in a rush and you need to do something fast, it's better to do it in Themax and then you do it. But if you want to learn, I think that doing this kind of theories are interesting.
Maybe a comment also for you said it's hard to simulate biconic surfaces. So maybe you can do two simulations for different conic constants and then somehow combine them, right?
Yeah, maybe something like that.
Yes, I would like to ask you, have you compared this to the Covington equations?
No, I didn't apply, but we can do it. Yeah, I didn't compare.
No other questions? Oh, yes.
Have you done any simulations? Have you done any simulation to know the distortion aberration and to compare?
No. No, as we were focusing to the refraction, just the refraction, we were ignoring in some way the distortion and the others' contribution. No, we didn't simulate it.
Yes, then we thank you so much.
Thanks to you.
Hello, my name is Fabian. I'm from Andreas University. I'm supervised by Professor Wisztonek. And I want to talk to you about the axial length, the corneal radius, and a little bit and about refractive errors. So first of all, I need to state exactly what is the axial length and corneal radius of curvature ratio. It's the ratio between the axial length and the corneal radius. So for emmetropic eyes, it's around 3.0 to get the right ratio. For hyperopic, it's around 2.95, and for myopic, it's above 3.05, but it really depends on the article. So the aim for this study was to create a refractive error prediction tool based on the axial length and corneal radius for two different eye models. So the eye models that they used were the Brennan and the Goncharov and Dainty. I worked on the real pupil size of 3 mm. I simulated different refractive errors based on the axial length and the corneal radius, point by point. For the axial length from 21.5 to 28.5, and the corneal radius from 7 mm to 8.5 for the monochromatic light. So the interesting part is this. It's the map that was simulated point by point for different axial length, as you can see here on the horizontal axis, and for different corneal radiuses. You can see the whole map that shows different refractive errors with some contour lines that go to the whole map and show on what exactly refractive error we are. For the visualization purpose, the map is divided by one diopter, but in the real simulation it was like continuous to the whole range. So first thing I need to tell about refractive power differences. So here we've got the same eye model, Goncharov and Dainty, but for two different crystalliness powers. And you can see that the powers are different. For example, just in this place, it's around 3 diopters of difference. This corresponds to the difference in the total eye power. So where the total eye power was different to around 2 diopters, the map just moves. But important thing is that the relationship between different points locally is always the same. So you can see that on the second map, in every place, the distance is the same, but it's locally because here it's larger and here is a little bit smaller to get the distance. Next, I looked for different for model differences. So I took the Goncharov and Dainty and Ubrian model. I used the same refractive power and just divided two maps. And you can see that still there are differences that correspond to the position and rotation of elements inside the eye model. The next thing that I could do, I looked for articles that show a lot of refractive errors with error bars, and I could just map those data to the refractive error maps that I created. And here, based on the Grosvenor and Scott data, I could fit my map by fitting the crystalliness power up to 7 diopters. So it's quite wide range of refractive errors. So as I mentioned before, the values on the contour lines depend on the crystalliness power, but the relationship, the differences of 1 diopter, remains the same, regardless of the crystalliness power. And for the next slide, this refractive error map values do not have the crystalliness power matching with experimental data. because in those experiments they didn't give information about the crystalliness power. So what we can do? For example, from the Hosna and Savini experiment, they gathered a lot of data about different ethnicities and stated that the mean value of axial length in the corneal radius is something like this and something like one and another value for male, female, and for both sex. So you can see that even if we've got similar values on the axial length and the corneal radius ratio, it doesn't correspond to the same values in refractive errors. So the same ratio could be is dependent on the two parameters, and it could be useful to just show how it changes. So based on this, we can create a predictive tool for those maps. So if we could just get some information about the patient, about their crystalliness power, and a little bit about the position of elements in the eye, can create a map, and from the current state of the of refraction of the patient, we can predict how much the axial length could grow from numerous articles, and how much will change in terms of refraction of the refractive error power. So based on this, to conclude, refraction error maps show refractive states of lights and how they are correlated with the real series ratio. The refractive error maps show how refractive error map may develop both from groups and individuals. They are crystalliness power dependent, and different ratios could have the same refractive state. And the emmetropic state depends on the power, and can differ for various ethnicities. And thank you for your attention.
Thank you so much, Iñaki. So, questions?
It's more of a suggestion rather than a question. Listening to your presentation reminded me of my own I just gave a few minutes ago. But there's really a critical difference between the approach that you've used and the one I have. In that, in your case, you're normalizing two anatomical parameters, right? The axial length to the corneal radius. I think it would be really interesting to take the other approach, which is to take your schematic eyes, reduce it to a reduced on model, and then look at the ratio between two optical parameters rather than two anatomical parameters.
Yeah.
Because it may turn out that one approach is better than the other, but you'll never know unless you do both. And it would be a simple thing for you to do because you've got these theoretical models to work with where you already know everything you need to know to get the perfect reduced on model.
Yeah, thank you. That's what it reminded me from your presentation. And I really hope that I could see it before, because it's gives me a wider perspective on my problem.
And I have also a suggestion when it comes to presentation, because as the eye grows, we become myopic, so the refractive error is actually positive, not negative. That's why you are correcting it with negative lenses. Just would be more convenient, I think, presenting it with a minus sign.
I have a question for you regarding how, if I would like to use this clinically, would it be enough to have data from a biometer? Because I don't get really the lens.
The problem could be that from biometry you get only the distance, and there is difference on the tilting of the elements. Right now I'm not sure how much it makes a difference, how much tilt makes like alpha diopter and so on, but with further investigation it could be really useful, especially for clinicians, to do it like this.
More questions? In that case, we can thank you so much, Fabian.
Thank you.